In this video, we return to the roots of our problem, which is solving differential equations. We've seen Laplace transforms applied to functions, both forward and inverse transforms, but we haven't seen where derivatives come into that. Fortunately, as you might anticipate knowing the Laplace transform involves integrals, there's a relatively simple rule for the transform of the derivative of a function. And here it is right here. There's some technical restrictions, but they're restrictions that are met for all the functions that we're working with. So the key thing is the transform of the derivative of some function is exactly the same as the transform of the original function, except with some extra factors thrown in. We get an S multiplier, and we have a subtraction of the initial condition. If you think of the information we're typically provided in a differential equation, we're often given with the starting value for our function, and that plays a role in this part of the transform. So this is the rule for transforming a single derivative of an unknown function f. As a quick confirmation of that derivative rule, we can look up in our table and see that the transform of cos of kt is s over s squared plus k squared. However, we should also be able to use that derivative rule. If we take the Laplace transform of cos of kt and remind ourselves that cos of kt is also equal to the derivative of sine of kt, well, not quite. We'd have to have a 1 over k out front to make that work. But if we differentiate 1 over k times sine of kt, we get cos back. And so what we could write that as, if we wanted to, is the Laplace transform of 1 over k times sine of kt, if you like, prime, as our new function. Using our new Laplace for derivatives rule, we can replace that with the 1 over k is a multiplier, it stays out front. The derivative is the next most important part. And for that, we take an s out front, and then we transform the original function, sine of kt here, the thing inside the derivative, and we subtract off sine of 0, the value of the function at time 0. And now we can simplify. So 1 over k stays out front. We have an s. We have the Laplace transform of sine of kt, and that is in our table. It's the k over s squared plus k squared. And sine of 0 is simply 0. And lo and behold, we have a k in the numerator and denominator. When we simplify, we end up with the same expression for cosine as we had in the table. This was derived from the definition, but this version here, which is identical, can be derived just as easily using the related rule for sine and the related rule for derivatives. This is typical in Laplace transforms, so there's many ways to get to the same transform value using the table. There might be different routes available to you, and one might be simpler than another. Our next issue is to consider higher derivatives. So if we have a function with first derivatives, second derivatives, all the way up to n minus 1 derivatives, and they're continuous on the interval we're interested in, which is out to infinity, piecewise continuous as well, and as long as they're exponential order, so all those caveats that we needed for functions to have Laplace transforms, then if we have this nth derivative, and we ask what's the transform of that derivative, we see the following pattern. We get the transform of the original function. That's what this is here. And that transform of the original function is multiplied by s to the power n. So however many derivatives, that's how many s's we get out front of that. And then we have a long series of initial conditions involved. And what we see in this pattern, and it's in your table, is that as we start, I think of it starting at the highest power, that goes with the f. After that, we have the s power decreasing. And also moving that direction, we have the f derivative increasing. So what we see is the first term, which has our transform of f, has the nth power of s, and then n minus 1, then n minus 2, until there's no more s's. Looking at the other term, the other factor in these initial conditions, we start off with the value of the function, then the derivative, then the second derivative, then the third and the fourth, and so on, until we get to the last derivative before the nth. And again, this is typical of the kinds of initial conditions we saw earlier in the course. Looking at the kinds of equations we've seen so far, though, the transform of a second derivative is obviously going to be something that appears fairly frequently. We've seen lots of second-order systems in our modeling so far. So with the second derivative, notice we have two derivatives, and so we have an s squared. S to the power of 2 is our leading factor out front of the transform, and then we have, again, the s decreasing as we move across, and the f derivative increasing. So we'll see how this plays out in terms of examples. It'll make it a lot more concrete then.